My name is Michael Baker, and I'm here to talk about finding these needles in haystacks the size of countries. And I suppose when I talk about countries, I'm really talking about the explosion of data and the exponential growth of the web, and starting to look at things in different ways because we're just getting flooded with so much information. And I suppose at the same time that we've got this rapid data growth and information coming in, we've also got to kind of struggle with these sophisticated and complex attacks. And I suppose the talk comes from how to find these motivated and sophisticated attackers in these kind of massive seas of data. I'm not sure you would have ever seen a talk like this before at Black Hat, but we'll wait and see how it goes. It's pretty complex in some areas with regards to technology, but I tried to keep it as technical as I could. I suppose the main theme is that the future is going to be fairly different to the past, in the sense that defending against these kind of sophisticated attacks will be more about how we detect and respond as opposed to how we try and prevent them. That sounds crazy when you think about it, but I'll get into it. So in 2011, I spent the year building a kind of big data security analytics platform to run in the cloud. We're close to finishing it, and at about the same time the call for papers came out from Black Hat. I condensed a lot of the ideas that I had for the product. We pitched the paper to Black Hat, it was accepted, and the only problem with that is we had about 2 to 3 weeks to build an open source equivalent of what the real product does. And it's the open source equivalent that we're releasing today at Black Hat Europe. 2011 was also, I suppose, the year of the hack. I saw a couple of really good tweets that kind of likened it to the late 90s. It's almost who didn't get hacked in 2011, with major brands, security companies, security consulting companies, etc., all being exploited for intellectual property, money, damage, etc. So we saw this kind of nexus between being able to find these kind of attacks. So just before I start, how many people here, just a show of hands, are directly responsible for the security of their organisations? Okay, yeah, cool. So we all know this story then. The CEO thinks the network is something like this. The Black Hats are this, or is it something like this? This is you. You burnt the roof of your mouth. And some consultants are obviously smiling at the proposition. And guaranteed someone's going to ask you to enhance.
Hold it. Run that back.
Wait a minute. Go right. There, freeze that.
Full screen.
Okay, freeze that.
Tighten up on that thing. Vector in on that guy by the back wheel.
Zoom in right here on this spot.
With the right equipment, the image could be enlarged and sharpened.
What's that?
It's an enhancement program.
Can you clear that up any?
I don't know. Let's enhance it.
Enhance section A6.
I enhance the detail, and I think there's enough to enhance. Release it to my screen.
Enhance the reflection in her eye. Let's run this through video enhancement.
Victor, can you enhance this?
Hang on. I've been working on this reflection.
Someone's reflection.
Reflection.
There's a reflection of the man's face.
Reflection.
There's a reflection.
Zoom in on the mirror.
You can see a reflection. Can you enhance the image from here?
Can you enhance it right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance.
Zoom in on the door.
Times 10.
Zoom.
Move in.
So I suppose, why is this funny? And in this one video, you've got a good metaphor for security. They're talking about enriching data, and we're generally dealing with the loss of resolution when it comes to security events. They're talking about play, pause, rewind, and they're analysing from different angles. And we're dealing with kind of isolated events that are there and then gone. And I suppose they're exploring through a vector space. And like I said, we're dealing with isolated data. The other couple of areas of this movie is that they're dealing with something that is in the past, whereas a lot of what we focus on is something that's, we're prepared for something that's going to happen in the future. And I suppose lastly, they're operating on a full and complete record of the event, and we're trying to piece information together. So in both situations, you're going to end up with people crowded around an individual who's meant to try and see the matrix and try and make sense or find an offender, and which is a very difficult task to do. So I'm not sure whether you believe this or not, but on a long enough timeline, prevention fails. It's exhibited in 2011 with the number of hacks. It's exhibited prior from the kind of people that are here at Black Hat. The development of 0 days, getting paid for exploits, etc. Prevention is a zero loss game. So based on that logic, detection is the key. And I suppose when we look at 2011, the RSA case is probably the best example of a tool that exhibited all the kind of characteristics of network security monitoring, or NSM, being used to kind of track down, look at, explore, and understand the events that happened at RSA. It was good enough to see the acquisition of NetWitness by EMC and RSA, and good enough for the CSO of NetWitness to be promoted to the CSO of RSA. So if you're not familiar with NSM, obviously Robert Baitlick's probably the most popular theorist when it comes to NSM. The analysis and escalation of indications and warnings to detect and respond to intrusions. And I suppose if you just break out the keywords of analysis, analysis of indications and warnings, detection and response are very, very important. Something that's quite akin to that is it's focused on providing an intrusion analyst with the best possible information in the shortest amount of time. Basically, a good way to think about NSM is it's everything that happens after prevention fails. Okay, and like I just said before, prevention will fail eventually. So there's an emphasis on detection. NSM, I suppose, devotees aren't really saying don't do prevention. All they're saying is, don't gear everything up for prevention. And what I'm really saying in this talk is that detection is going to be the key to finding attackers in the future. They believe in inventoried and defensible networks, and also building up entropy or understanding of attackers and attacks. Providing analysts the key information, and also, I suppose, putting people in the forefront. NSM's or network security monitoring has often been criticised for how people intensive it is, or resource intensive it is. And when you think about that, it's like having CCTV or red light cameras and not having police. At the end of the day, we've largely taken a back seat to the products we buy, and ultimately everyone who raised their hand before is exceptionally important for the future of security, in the sense of being analysts to find attackers. The kind of NSM tools that some of you might be familiar with on the screen, they're all akin in the sense that they can all operate on live network data or packet captures. And obviously one of the key concepts of network security monitoring is that tools provide collections and humans provide analysis. So it's all about context. Getting as much information to an analyst as quickly as possible. Now, when I say analyst, that's not the person at your work. That's you. Okay, the person who has to understand security events, interpret them, and then I suppose track down where was the breach, how long were they in there, what did they take, how do you clean up. This is what our CMs do now. They correlate information on time and source, destination port, source IP, etc. And maybe some of you are thinking, well, I don't even have a SEM. There's this concept I'll talk about constantly about going back to the well. Really what we saw in that enhanced video is the ability to kind of go back, replay, look at it, you found some new information, and go and retest your hypothesis again. And I suppose if you were doing real analysis, you'd want to branch your analysis, you'd want to think about different things, you'd want to wait for a response on some information and then re-explore. And what I'm talking about is no loss of fidelity. So what often happens is when we're dealing with logs or log management, we eventually roll hours into days, days into months, months into years over time. And what I'm saying is a key concept of analysis is not losing any of that fidelity and not abstracting any of the data. I'll just give you a brief example of context. So if I just spin this globe around a little bit, what should be happening is your mind should automatically be trying to work it out. What are all these lines? What do they mean? Why are they coloured differently? I'll just zoom in and zoom out. Now, if I give you some additional context, that this is a 420,000 snort security events in a 12-day period. Okay, and yeah, it's pretty interesting. And then you think that the lines are coloured based upon snort severity, and obviously the height above the ground is frequency. Okay. Just want to zoom in on South Africa. Zoom. Yeah. So I've got Johannesburg and Cape Town there. I'll come back and talk about those a little bit later. Now, I've provided you not a lot of context, but I'm also trying to make the key point is that when we try and visualise and encode data, especially big data sets, it's important to let the brain explore. It's important to analyse these data sets, and I'll come back and talk about these a little bit more in a moment. By the way, that 3D globe is courtesy of Google. We just modified the code to use with Snort. Full packet capture is the mechanism by which we can pause, replay, fast forward, and retest hypotheses over time. I'm not sure whether anyone's doing full packet capture at the moment, and what I'm really referencing is that you are either taking your internet connection or key segments of your network and dumping it to disk as packet captures. It's low tech, it's low cost, it's biodegradable, it's carbon neutral, well maybe it's not carbon neutral. It's also a key technique when you're under attack. All of the vendors, I suppose, would like to say, well, whilst you're under attack, why don't we deploy this or deploy that? But really, if you're under attack, the best thing you can do is probably go and buy a 3 terabyte USB drive and plug it in somewhere and start dumping PCAPs. Because at the end of the day, that's probably how you're going to find out exactly what happened. So here's a formula. And somewhere a math teacher just died. And what I'm really trying to do with this bad mathematics example is say that NSM, network security monitoring, plus full packet capture gives you the greatest percentage of options. And I'm also saying with my bad arithmetic that without full packet capture, you won't be able to unmask or find these sophisticated attacks in the future, or now, or for the past couple of years. So I will eventually get around to the technical part of the talk, but this is the build-up. The difficulty shifts, as Robert Baitlick says, from just capture, and you can buy 10G capture cards and you can get cheap storage and there's all sorts of things you can do. The capture's not the problem, the analysis is the problem. And I suppose there's no tool on the market at the moment that can easily work a 2 or 3 terabyte data set or more, 100 terabytes, 200 terabytes. Well, there hasn't been until you start to play with it today. So let's devise a system that solves the problem. We've got all these storage nodes, and I just want to apply my packet captures to the storage nodes. I want to ask questions of the compute node, and I want them to do some really cool magic and interrogate the PCAPs on the storage. And then what I want to do is I want to grow that horizontally so that it answers my question within a particular period of time. Now, you can think of it about it as well as I want to ask a 2.5 terabyte question. And the data set that I'm mainly talking about today was 2.5 terabytes, around 3 billion plus packets, hundreds of millions of conversations. What else did I want to tell you? 12.49 day period. Now, if I ask that 2.5 terabyte question and it comes back in 8 hours with 4 compute units, I might be happy with that. That might be the batch process that I do overnight that gives me all of the information I need for the next day. It might break down snort severity, it might break down snort attackers, it might geocode or georeference particular IP addresses. But I might also want that in 4 hours, so I'll just use 8 compute units and so on and so forth, right? Now, the way that we've devised the system is that it scales in a linear way. Now, the one that we use, I'll discuss in a little bit in a moment. Now, everyone's now thinking, where do I get 128 compute units from? And what I'm really talking about there is once you start to get into that kind of scenario where you need to analyze 2.5 terabytes in 15 minutes, you're probably looking at something like Amazon's cloud with elastic MapReduce, and I'll talk about that in a bit more detail. You can think about it like this. Now, you can times all of that by 4, and you'd be able to answer or work with a 10 terabyte data set in potentially an hour using 128 compute units. Okay, so when you think about full packet capture, it can't be done, it's not workable, it's too much storage, you can't process it. We're going to show you how to do it. So really where distributed processing started was a Google MapReduce paper that they published in 2004. They were using it already for their PageRank algorithms. It was basically a way to use mappers and reducers, keys and values to distribute jobs across multiple nodes, giving you horizontal scalability on, let's say, commodity compute. They also published the GFS or Google File System white paper to speed this up a little bit. Hadoop eventually open sourced a lot of this as part of an Apache project. They also mimicked the nature of the Google File System, and then a data analysis query language called Pig came around in about 2008. So here's the answer to the question. I want a whole series of Hadoop nodes that also have HDFS. HDFS is the Hadoop file system that I copy my packet captures to. I ask a query of all the Hadoop nodes and they give me answers. I write the query in this thing called Pig Latin, which funnily enough is the language of Pig, and I kind of go from there. So it sounds like magic, but works. So the way to think about Pig is it abstracts the complexity of building MapReduce jobs. And it's not a SQL structured query language type language. It's more of a transformation language or analysis language where I group things on keys and iterate over values. And it takes a little bit of getting used to. And what you end up doing is just brute forcing it. And what I mean by brute forcing it is you just try it so many different times that you end up understanding the system. And Pig is made up of loaders which extract the information out of PCAPs and present it in via a schema to the script. Types, it has scalar and complex types. It has these things called user-defined functions, which we use as well to do things like georeferencing, GeoIP. The majority of the system is built on Java, but you can also, we've also wrapped Python scripts. We've also wrapped binaries like P0F and Snort to do exactly what we want it to do. Pig Latin's a pretty good language with regards to data analysis. You can group on keys, you can iterate over values, and it works really, really well when you start to work across packets because normally what you'd want to do is group all of source IP with destination IP, or all of source IP with destination IP and destination port, or all of the data where the SYN bit is set and the FINAC bit is set. Okay, weird kind of things like that. And Pig will just then take that query, push it across to the Hadoop cluster, and then execute it. I'll talk a little bit more about this a little bit later. So the system we built was Packet Pig. We come from a company called Packet Loop. Pig was the query language, so Packet Pig was born. We open sourced it as of about a couple of hours ago for you to download and work with. It's open source, big data security analytics, and the way I really wanted to build the project was that it was a one-stop shop for network security monitoring. So all those tools that I showed you before, like Squeal and Argus and FlowGrep, etc., they're generally used as isolated tools on very, very small packet captures as these kind of electron microscopes. And what I wanted to build was big data NSM, and this is what the project allows you to do. You can also integrate logs if you want, like firewall logs, IPS logs, etc. If you want to join that to what you've got in full packet capture. I'm not anti-logs. I'm just saying you can do it all with packet captures anyway. And a key part of the project as well was to focus on some visualizations, which are excellent ways of encoding data and keeping people interested. So some of the Packet Loop features. The first thing you might want to do is just like Wireshark the internet. And I say that facetiously a little bit in the sense that this tool already works on terabytes of packet captures now. So if you want to scale that, and we run on a cluster at work, which is 4 Dell 1950s that we bought off an auction site. Okay, and we can process close to 3 terabytes of data quite quickly whenever required. So all of these things I'm going to show you, how to bin time, how to do threat analysis, traffic analysis, conversations and flows, geolocation, operating system fingerprinting, and file dissection. Now, all will be demoed today. So if all those people that walked out before, no, I'm just joking. Okay, so the way to think about this is all of those functionalities are implemented as loaders. Now, what I said before is that loaders kind of go into the PCAP, they extract out of the PCAP, and they deliver it to our scripts based upon a schema. And then those schemas I can do all sorts of magical things with. So, when I said we have raw access to packet captures at terabit scale, or terabyte scale, that's there at the moment. You can filter, group, sort, you can count, you can average, and that gives you the ability to do things like get bandwidth by TCP, get bandwidth by UDP, get bandwidth by ICMP. You can get bandwidth broken down for every single source. You can get it broken down by every single destination, and then you can link the two together for every source and destination, or every source, destination, and destination port. So all these queries are really, really easy to write, and then you get all of the information you need quite quickly. The other thing you could do is search big data sets just for weird kind of TCP flags, etc. Now, we're going to go a bit deeper than that. So I'll just show you an example. Can everyone see that? So when you go and git clone the repo, you'll get all of this data come down, and there's an area or a whole series of files in pig examples, and this is the first example. It's called basic packets, okay? And it doesn't come any more basic than this. So I described before that there's these things called loaders, and we've written one for you that extracts the PCAP data. And then from there, it builds it into this schema. And the schema should look fairly familiar. Timestamp, IP version, IP header, type of service, etc., etc. Now, you notice there's all the TCP fields there as well, and all the UDP fields are there as well. At the moment, we didn't do ICMP. So if you're looking for that, help us out. You can help us write a loader. So I then take it from there and I want to run it. And pig, I'll just try and get this so you can look here. What I'm saying here is I want pig to execute the following file, -f, pig examples basic packets. Now, I want it to process across the PCAP called web.pcap, which is in the project, and it's just a tiny little PCAP for you just to make sure you got things right. The beauty of Packet Pig is you can write all your queries on your laptop using pig execute local, and as soon as you've got the query right, you can run it on a cluster. So if you've got the cluster sitting at your work and you think that's where the 20 terabytes is, but I really just want to get every single GET request from this source against this destination for the last 3 days, and then you can write the query locally, submit the query to the cluster, and it comes back and gives you an answer. And it gives you the answer back in the same shell that you were just running. Now, one of the things I just didn't kind of go through before is when you run these scripts, you can do things like dump or store. Now, when you dump to the screen, you dump to standard out. When you store to the file system, and that file system is the Hadoop file system or your local file system on the laptop. Let's just execute this. Now, you look so geeky because of all this kind of information that you get, but that's just Java, right? So I'm just going to clear that screen. It's still running. And eventually I get full access to the packets, right? And if I go and highlight one, you'll see a Unix timestamp, you'll see IP version 4, you'll see the header length, you'll see things like the source and destination IP address, etc., all built out in the packet. Now, if I wanted to, I could then go back to this script and edit it for whatever I want. I could filter based upon SYN bit being set, I could count the bandwidth, I could look for just TCP protocol version blah. It does work for IP4 and IP version 6 at the moment. Okay, so that's just basic access to packets. One of the first things you probably want to do is start to bin time. What I said before is most systems built today working on logs, certainly if they use relational databases, they start to bin time, they start to aggregate things. So they roll minutes into days, days into months, months into years, etc. With the packet capture sitting on the Hadoop file system, you have the luxury that you can bin time in whichever way you want. And all of our scripts allow you to bin time based upon a variable you pass in. So if I want to count bandwidth every 60 seconds for the last year, I can do that. If I want to count it every hour, I can do that. If I want to count it every day, I can do that. So sometimes you'll want to run a job and output particular bin widths based on, I've just got some examples there, 5 minutes, 30 minutes, etc. So any of the loaders that give you a timestamp, you can bin. You can bin snort. You can bin anything that we can send back to you. So just to get you familiar with it again, I'm using the packet loader. I've got the same script, and then that's complex. I'll come back to it. Now the default time is that I want to bin on 60 seconds, and I've got another example there. Where I want to bin every hour, but the dash just means it's effectively commented out. Now, this job is using a store command, and if I can kind of go through this, I'm filtering on TCP, which is IP protocol 6, UDP 17. I'm then grouping all of the TCP, and I'm grouping that into a bin. So I've got the timestamp. And I've then got 60 times 60 in this case. So I want to bin it in 60-second increments. What I'm then doing is all the TCP information I'm grouping into a key, and then I'm summing the length of the TCP. I won't go through all of this, but basically, if it's relatively intuitive, you can see that I'm counting all of the bandwidth for TCP and UDP. Now, the store command just says push it to the file system based upon a comma-separated field, and the output is binning. Now, one thing you need to do is just make sure it doesn't exist first. And then I'll run the file. Now this is going to bin all of that information in 60-second increments, and this is a kind of batch process you normally wouldn't watch, but it's going to push all that data to the file system. So if I go and look at output binning, you can see that I'm using a very, very small PCAP here. So I've effectively got one bin. If I go back and change it to an hour and use a bigger PCAP, I can bin in any increment that I like. Another thing we did is we wrapped Snort. So Snort has a -R feature, which allows you to parse it a PCAP, and it allows me to run Snort distributed across Hadoop nodes. So all the PCAP information that's sitting there on the file system, I can use Snort based upon any rule set that I like. One of the things that we like to do is we like to run multiple different Snort rule sets, and I can pass the snort.conf as a variable when I execute the script. Snort returns me the timestamp, the signature ID, the priority message protocol, source port, destination IP, and destination port. So that's the schema that's returned by the Snort loader. This is handy for finding zero-day threats in old data. So remember, Snort is a signature-based system mostly, and as I update my signatures, I have better view of the past in the sense that if I go back and rerun it across a whole series of PCAPs, I can find 0 days in old data, which is obviously important for analysis. The other thing that we did is we added geolocation. We wrapped the MaxMine database, which means that we can do geolocation off the disk and we don't have to call that to any web service, which is pretty handy, but use wisely. The free database is not exceptionally accurate, and I've got an example of how I messed that up. Okay, so we showed the 3D globe before, and I'll just explain a little bit more this time. So one thing that's nice about the 3D globe is it is just basically the output of a job, which gives me lat long, severity, and count. So if I just go back again, I can quickly have a look. Now, I'm not expecting that analysts would drag this information onto a web page. What I'm expecting is that you run a whole series of batch jobs, and then you come to the website, and then you have a look at it over different periods or days. So yeah, I'm not advocating this drag and drop method to security analysis. So once I've got that, I can obviously look around the globe, but I can quite quickly have a look at alternative data. So these are two different organisations we work with, and obviously fairly different in the sense that the data sets are, one is way over targeted compared to the other, and if I told you who they were, you'd know why. Okay. The next one I'm going to show you is another visualization we've got to kind of look at time series data. Now, all of these come with a project. So, now I'll just show you the data again first, and then we'll go back to it. So, we've got a number of scripts in there that output severity, country, timestamps, and then the count. So this allows us to quickly compare countries to each other. Now, this uses the D3 JavaScript framework, which allows us to build kind of pretty visualizations, and you're free to extend it and do whatever you like with them. So obviously, this one is around 54,000 attacks from Australia. We kept the same height, so the highest value is the highest in the field. So China 110, the Netherlands is represented there as well. These are all attacks against an organisation we work with in Sydney. So as you'd expect, everything's local. That's quite weird, isn't it? Okay. The third kind of visualisation we built in for Snort is a thing called a choropleth, which you're probably familiar with if you've used things like Google Analytics. And again, the choropleth allows me to quickly look at things like severity by country. Or it's a slightly different look. There's different customer in, or different organisation, I should say. That was threat analysis. So by wrapping Snort, it gives me full access to an IDS system. I can then go and take any information I pull out of Snort and go and mix and match it or mash it up with other data that I get. Traffic analysis is also kind of coming to the fore, especially in the area of identifying what's in things like encrypted tunnels, or what information or protocols are being tunneled inside of other protocols. Now, I'm not sure if you've seen, a good example of this is at the Chaos Communications Conference. There was a guy there, Stephen Bershka, that showed packet size and inter-packet delay of Skype. And you may have seen this. If you haven't seen it, go and watch it on YouTube. It's a great talk where they use packet size and inter-packet delay to infer what was being said across an encrypted Skype channel. And you could start to do similar kind of things with Packet Pig with not a lot of modification. Packet size has been used for a while, and there's a good thesis, traffic analysis of SSL encrypted web browsing by Cheng and Avner, and also another one there, which is n-gram analysis. Basically what these guys are doing is taking features out of packets and using those features to understand what's being said in encrypted channels. If you're not familiar with n-gram analysis, it basically is a window that we slide across the data in any number of grams. And grams, what I mean there, we do unigram, bigram and trigram generally. So unigram is basically me going across the data of the packet and looking at all the ASCII codes, and then looking at whether ASCII codes are similar between different protocols. I can also then do bigram or trigram. Trigram is very, very good at semantic type analysis, like things like HTTP, and I'll show you some examples. Packet Pig can do any number of n-grams. So if you just want to pass it to the script, you want to do unigram, you send 1. If you want to do trigram, you send 3. If you want to do more than that, you can as well. So let me just show you a little bit of n-gram analysis. So what I'm showing you here is a breakdown of protocols. Sorry about that. Based upon unigrams. So what I've done here is I've taken all of the different ASCII codes from 0 to 255, and I've arrayed them from the left side of the x-axis to the right side of the x-axis. And as you can see here, this is all in blue, TCP is 80. HTTP is 80. And then if I look at HTTP and HTTPS, they're not too dissimilar in the sense that I get a pretty fair distribution across all ASCII codes for the protocol. Now you're wondering where I'm going with this. SSH and SMTP are fairly different. SSH and DNS are fairly different. Now, what you're seeing here is a lot of use of DNS in the lowercase and uppercase range, which you'd expect, right? So that is kind of normal DNS traffic. And then lastly there I've got SMTP. And again, because we're probably familiar with it using upper and lowercase letters, it has a distribution which is fairly unique. Now, the reason why I'm showing this, as soon as you show it in histograms, you start to see how many characters they use in general in any given packet. And we can do things like probability analysis to understand if I'm seeing traffic on a particular protocol, I can understand whether it's DNS or understand whether it's SSH. So the way we wanted to build PacketPig is eventually you could go through an entire data set and say, well, hang on a minute, I'm seeing SSH on port 80, I'm seeing HTTPS when it should be this, I'm seeing this, different protocols on different channels. One that's pretty cool, and it reflects one of those studies, theses I just showed you before, is SSH. You generally won't see SSH use any more than 80 characters in general, okay? So you can make pretty good probability statements as to what is SSH. Now, these scripts are available in PacketPig right now, and the visualization's there as well if you want to play with it. So that was unigram analysis, okay? I'm taking the data, I hope everyone's got me. I'm taking the data out of the packet, and I'm counting all the zeros, ones, two, three, fours, etc., all the way up to 255. Now, ASCII character codes, where we would kind of expect English, are generally up around the 100 mark, okay, for lowercase and uppercase text. And you can kind of see that there, if I take that off. Another kind of n-gram analysis, and it's difficult to kind of demo, is trigram analysis. Now, again, if you go and check out a lot of the kind of work that's been done in the area of papers and theses, you'll find some of this in the research community. Now, I'm just trying to situate the cube a bit. Now, there's no way you'll know what protocol it is, and I only know it because I dragged and dropped it, but it's SSH. Now, it's a little bit difficult to see with regards to that brightness. No different. Okay, so what I've basically got here is three axes. I've got Z, Y, and X, and each one of these axes is 255 characters, grouped into lots of 16. And this is a kind of good visualization or kind of experiment in understanding protocols based upon a three-dimensional kind of model. We also built in deep packet inspection. So for DNS and HTTP, we can go right into the packet, pull out features, semantic features of the protocol itself, and kick that back to the scripts. Just give me a sec. I'll just show you this script first. Note the use of the DNS loader and then also the schema. So I can see the timestamp, I can see the query ID, and the ID is also returned. I can then from there see any kind of DNS name, its IP address, and its TTL. The reason why I'm showing this demo is there's a lot of malware analysis that's being done at the moment where they do things like look at changing TTLs across domains, or they look at the actual name of the domains themselves and how deep the domains are. So we built this in case you wanted to kind of go across big data sets and start to explore whether DNS gives you some features that you can use to identify attackers. So I'll just I'll just run the DNS one quickly. Just going to change my PCAP to a slightly larger one. That's the percentage complete. No, I'm going to do a small one. It's a problem with doing demos. People like them, but okay, so you can just see here quite quickly all the timestamps, all the queries, all the responses, all the TTLs. I could then go and graph TTLs. I could go and look at different domains. I could look at travel across domains, and I'll show you an example viz of that in a moment. HTTP works very, very similar. If you wanted to get every single GET request or every single user agent, you could quite quickly do that with the scripts you've got here as well. So all this is going to do is go through the same relatively small PCAP and expose all of the HTTP features for you. Because I chose store, I'll just go and look at that quickly. This is just some examples. So over on the right, I've got every single request. I've returned a schema. If I wanted a group based on gets, if I wanted a group based upon user agents, if I wanted a group based upon URIs, I could. I better speed up a little bit. This is a visualization that we included with PacketPig. It's a visualization done in R looking at TTLs. And basically what I've done is I've got the TTL along the x-axis down the bottom here. Sorry for the black hat badge. And what I'm looking for here is any travel from right to left or left to right. And what I mean by travel is when you see domains rapidly change their TTLs, they'll have a number of different stars in this visualization from left to right. And often that's an indicator of either polymorphic domain or lots of domain changes, of TTL changes quite quickly. I might skip the Ubi graph, but no, it's cool. We'll show it. So another thing you might want to do with DNS is look at how deep domains go. This visualization again is included in the repository. Now, the reason why I'm resizing Windows is as soon as you kick off the script, Ubi graph builds. Now, normally you wouldn't do this for big data sets, but what you might do is you might want to break down particular individuals that are making really weird queries. So I generally wouldn't see this done across a million queries or a billion queries, but what you might do is break every single source IP address that ever did a query and do a little bit of a visualization for each one of these if you wanted to. That's just Akamai, but if I started to see really long domains or weird domain names, the viz is a bit experimental at the moment, but it kind of gives you some idea of where you can go in the future. Because we adhere to normal NSM type or network security monitoring type tools, we can break down conversations and flows. So if you wanted to group by conversation, output every packet from a conversation, packet size or inter-packet delay, we can do that as well. We also wrapped Michael Zalewski's P0F because it's really, really important sometimes to understand the operating system and other information of attackers. Now, P0F is an excellent tool. We use a thing called Fingerprint Loader to output all of the details from P0F in a single line. One thing that you generally would want to do is compare P0F to HTTP user agents. Okay, so you wouldn't normally expect particular user agents on particular operating systems. So they may be fudging the user agent, but obviously P0F tells me their real operating system type. It also passes through uptime, MTU, all of the. If you're familiar with P0F, it's the same output. I'll just give you a quick look at P0F. And then it comes out and tells me the wrong answer. That's a snort log. It's telling me that I've got TCP anomalies, which is not exactly what I wanted to understand right now. But thanks for coming. At least you know snort works. Okay, and there's all the P0F data. If I just take out one line, you can start to see that I've got what I would normally expect to see for a particular record, source IP, destination IP, that it's Linux, that it's on an Ethernet or modem, its uptime, etc. We can all get that straight out. File extraction is particularly awesome, and probably the first thing you do when you've got big data sets, because I don't know about you or myself, I'm always interested in images. So normally what you would do is file extraction. The file extraction utility allows you to report on the files, extract files by MIME type, report on the files based upon a particular MD5 or SHA-256 hash. A lot of what you might want to do is not really extract, but just go through terabytes of data, find every single file and every single application and every protocol, and just output the hashes, and then take the hashes to something like a third-party reputation service like VirusTotal. It's a good example. Now, it outputs in a kind of weird way. I've got to watch time here, so I'm going to cut some of these short. And I'll just show you the extracted files. So this is on... Now, we changed this code recently so that it outputs the file name itself as well. But you can see all the different hashes are there. This is merchandise for a soccer team in Australia. I won't go too low because the files start to get particularly dangerous as I go a little bit lower. So I'll just stay at those top ones. I learnt this when practicing because that's not the kind of thing you want to show. Just to show you the file output. Remember, you're running this across very, very big data sets. And often what you just want to know is just, we also wrap libmagic in here as well. So if it's a file inside of a zip file or gzip or tar, or if it's an exe, we can get particular information from libmagic as well. So sometimes you just want to, well, hang on a minute, it's a PDF, but it's really an exe, that kind of basic stuff. I don't know if anyone saw Didier Stevens' workshop today on PDF analysis. We could easily wrap a lot of his PDF tools using Python into this and do PDF dissection across terabits of data as well, terabytes of data. Done. I just want to pause for a moment. What I've basically showed you is thread analysis, traffic analysis. I've wrapped P0F. I've got deep packet inspection. I've got all these building blocks that you can use to do analysis across big data sets. And when you start to play around with this stuff, it starts to become a little bit worrying as to what you can get and how much information you can extrapolate. And it kind of got us to thinking that that is big data, big surveillance, and really packet capture is analogous to wiretapping. When you start to play around with packet pig on big data sets, you'll start to see the kind of things that you can do, and obviously potential for misuse without discretion is particularly worrying. Now, maybe a little bit of a glimpse to the future where all packets are analysed and big data sets are kind of exchanged as dossiers or data reservoirs is particularly worrying. I suppose we're here now in the sense that that I've kind of built the tool that I'm worried about. But I'll give you an example of how crazy this can get. I figured some of you may be partial, some of the locals may be partial to this. So my simple experiment is I wanted to go and take a very, very big data set of IP addresses and cross that against everyone that attacked me in those 420,000 attacks in 12 days. And then what I wanted to do is see whether I could get any additional information out of a third-party IP data set that would give me any more information on my attacker to understand who they were or what they did. So part of this, I should give credit as well, was the You Have Downloaded website. I don't know if you've checked it out. but they were obviously tracking torrent leeches and seeders for a long period of time, and then you can kind of go there and see what's been downloaded from your IP address. If you go there right now on the Hotel Wireless, you'll probably see some interesting stuff. So what I did is we connected to, as well, if you're getting a bit squeamish, I'm not going to show any IP addresses more than a Class A in the next kind of demo. So I won't out anyone. So I connected to the top Pirate Bay. I think I did movies, books and music, the top 100, and I downloaded every single IP address of a seeder and leecher that I saw within about a 2-week period, thinking that maybe some of them also attacked me in those 420,000 attacks. It was a long shot, but I'll show you what else we did. We also took the BitTorrent client. This is a particularly interesting part of entropy because I don't know if you knew this or not, not being a torrenter myself, is that your BitTorrent client version number, etc., is all reported and all publicly available, which you may or may not know. And if you're particular versions of uTorrent or Azorus or transmission, it gives away some good information. Remember, I've also got P0F. So I've got P0F to tell me your operating system. I've got your user agent potentially if you touch one of my websites, and I can join that with snort data, etc. And what I wanted to work out is where the torrent data would allow me to triangulate. So particularly one of those kind of problems you always try to solve is if I've been attacked by the same person, by the same attack, but they're on different IP addresses, how could I kind of infer that they are the same person? And I'll show you how to do it. So 420,000 security events over 12 days, 3 billion packets, total data size of 2.5 terabytes. There was 1,890 sources of attack against the people we were working with, and we downloaded around 170,000 torrent peers. So we had 1,890 attackers, distinct attackers on IP addresses, and we had about 170,000 IP addresses that we got from the Pirate Bay Top 100, which is a decent join in any database. 17 IP addresses matched attacks and also matched the torrents, which we were a bit surprised by. I never thought that we would get it, which meant that I was up till very late the other night trying to finish these slides. So mostly from Australia, China, South Africa, Philippines and Singapore. Again, this victim was in Sydney. So when I say that all, majority of attacks are local, in the sense that geographically local, it keeps coming up in all the data sets we analyse. Mainly protocol anomalies and spyware upload detection was what I was getting from Snort. 2 cases in particular are worth going further. Now, again, I'm using all the information from Snort. All the information from the torrents now. I'm getting all the information from P0F and user data. Can anyone see a problem here? That you're happy to attack me, but you're prepared to download Footloose. And it's not even the original, it's the remake. So these were all the torrent files, and I'll show you the actual data if you like. This creepy spreadsheet. IP address is A and hidden, but these are all the torrent hashes. These are all the, so each one of these rows is an IP address, a distinct IP address that attacked me. These are all the, notice the 7 weeks to 100 push-ups, I love that. And these are all the countries, these are all the AS numbers, these are all the lat longs, and this is all done from one packet pig job across 2.5 terabytes of data and all the snort and all the torrent information. And I'm going to have to rip through this. So I've got 2 cases now, and they've got some severe crime. Sorry.
It looked like they were targeting on the Vodafone wireless connection.
The Vodafone one, there's one from Australia, which is which may, well, the one I'm going to show you from Australia looks like it's it's Vodafone here. Where'd you get the wireless from?
Vodafone only have wireless
In Australia.
in Australia.
Oh, okay,
Yeah, they don't exist.
that's very interesting. Okay,
Only through Google.
we'll come back to that because you might know something I don't. Which
We can have a chat.
yeah. The South African and the Australian. So I'm going to run down 2 of these cases. Now, they don't have any kind of serious crimes against me, but this is to kind of show you what analysing big data sets, it can get a little bit scary. So the South African, there was 9 IP addresses from SAIX.net. They all matched up to SAIX proxies. The attacks that I saw from South Africa were long headers and spyware. Now, the spyware alert, that's the actual way it comes out in Snort. It kind of worries you a bit. You're like, oh, spyware put, oh, they're trying to infect me. And I'll go a little bit further into it. So let's enhance. So I pulled out the lat longs of these IP addresses, but they were relatively useless. They either came out of Cape Town or they came out of Johannesburg. And they did kind of match to houses, but I didn't really want to show their houses. But anyway, what I did get was a correlation between 7 weeks to 100 push-ups linked 2 IP addresses to each other. So what I can do is I can say, well, these 2 IP addresses attacked me. I saw those 2 IP addresses also downloading the exact same torrent. And if I was particularly crafty, I could look at the percent complete on the torrent and kind of infer some information from there. And I also have entropy from the torrent client. The Adventures of Tintin matched another 2 IP addresses. And what I've basically worked out here is that I've got 2 attackers. When I got the P0F, when I got the user agent, when I got the snort data, when I got the torrent data, I can get a lot more information about attackers. So can you use third-party data sets to do things like triangulation? You can. It was pretty innocuous in the end. And I know this is a bit of a, not as interesting if it was a kind of really kind of dangerous attack, but a lot of the times in security analysis, you just really want to get over it quickly, in the sense that I want to understand everything about that attack. It's a non-issue, move on. When I went and Googled the IP addresses, they were linked to known spammers, and again, I've blocked everything out just in case it was some, and this is actually a site where someone said, I've actually got a legitimate user, but he's being blocked. And what they're being blocked from was their user agent. Their user agent down the bottom here shows that they're infected with some kind of malvertising spyware. The key there is Trident 4.0 and Fun Web Products. If you go and Google that, it's part of a spyware campaign. And a lot of people in South Africa were infected with it. So moving on, POF told me that those IP addresses were linked behind proxies that were OpenBSD. Looking at all of their HTTP requests, I could see their user agent and I could pick out distinct entropy with regards to the user agent. And then from there I could work out that it was just probably some at-home PCs infected with spyware and malware. The Australian one is a little bit different. Okay, so their attacks read crimes. In this scenario was just some protocol anomalies, but let's track them down. So GIOP gave me lat long. I built a packet pig query which gave me all the data I needed, and then from there I also cross-referenced it with the torrent information. Let's enhance. So this is part tongue-in-cheek. So what I did is then commenced a 6-month stakeout of their house. Now, I should say that all of these maps are provided by an Australian mapping service called Nearmap. It's really incredible with regards to their resolution. And also they do mapping over time. So if you see up the top there, I can go back 12 months or I can go back 1 month. They generally fly every area in Australia every 30 days. So like I can tell here, there's a red car. Right? And on the next month, there's no red car. And then from there, lots of white cars. Now, I then go and take the same lat long. Maybe there's a reflection there, I'm not sure. I take the same lat long and I go and plug it in to Google Maps. And then I hit Street View and there's my guy. Now, I'm obviously being quite facetious in the sense that if this went to a court of law, that dangling A above his head would be exceptionally incriminating. But the free version of the MaxMind database is not very, very good with lat longs, and it was actually a totally wrong address. So just before calling the police, I actually linked the IP address to a university in Queensland, which is, for anyone that knows, is about 1,000 kilometres away from where I originally thought it was. Now, then it started me thinking, well, who else knows about this IP address? And then if you ever want to look up an IP address, Google this query ORS stats and then the IP address, and you'll see everyone's kind of logs that have never been locked down, and you can go and look at all their queries over time, and you can build this kind of chronologue. And I did this for the South Africans as well. I just didn't bother showing it. And note, I've taken the IP address out. It's only showing you the first octet in all of these examples. Also see that they're into baby slings, and every query they ever made on the baby sling site. And then also that they like to vote on where the next strong VPN server should be situated in the world, etc. So The moral of the story is that big data can start to worry you when you start to process these data sets and get all this information. You can kind of spin off quite quickly based upon some error or grievance, and I'm going to have to wrap up pretty quickly. Anyway, in both cases, all the information that I gathered, it was very, very quick to gather, parsed the entire data set, looked at every single DNS, HTTP query these sources ever made. I could look at their protocol distributions, and then I could make decisions as to whether they were valid users or just, like I said, poor people that had their home browsers infected. They didn't justify any additional kind of queries against the data set just for the fact that they were relatively innocuous. So what about Tor? Now, we did do this, and would you believe not one single Tor address was linked to an attacker against that data set, which is pretty interesting. I probably would have expected at least one. So some of the future features for PacketPig, I didn't show it today, but statistical analysis. Certainly starting to look at things like probability distributions and getting into more of the detail mathematically with regards to whether something is a protocol or not, or this type of protocol or not, is quite important. Machine learning, which we do a lot of, can start to do things like k-means or use the vectors that come out of particular queries to do things like link attackers to each other based upon distinct attack types they use, number of attacks per minute or per hour, geography, etc. We could also wrap a lot more NSM tools to give people, I suppose, more breadth across bigger data sets. But some crazy stuff you could do with this is sentiment analysis. I could take every single SMTP email and break it down as to whether it was positive or negative, and then just look across data sets for what's positive and what's negative, which is relatively scary. There's a library called Ticker which you can use to download all the text out of every PDF that passes the data set and then do sentiment analysis on it. You could also build up Lucene search indexes. One thing I didn't do in this was build a persistence area. So I didn't build a database for you to pump all this data into. I kind of left that up to you. You can either pump it out to text or viz or etc. Any questions? You've only got drinks now anyway. Yep. Sure.
You said that SSH uses a very narrow range of characters.
Around about 80.
Yeah, that seems kind of odd, seeing as it should be encrypted, which means it should be the full range of characters.
Yeah, you would think that SSH would use close to 255, or a universal distribution across 255 characters. It doesn't. It uses a very short subset. Now, that data that I showed you, how I did that frequency analysis on it, one of the papers that's in the slide does the exact same frequency analysis, and I compared my diagram to their diagram. It's almost identical. Yeah. The latest version of the slides will come out of the Black Hat site. The ones on the CD do not match these. I totally rewrote them. Yeah. Any other questions? No worries. Well, thanks for coming along.